Great. Hello, everyone. My name is Pauley. I'm a PhD student at Penn State. And the work I'll be discussing today, which is in collaboration with my colleagues and my advisor, Dr. Patrick McDaniel, explores the risks of IP address reuse on public clouds. Now, public clouds have revolutionized the way that organizations manage their computing infrastructure. By eliminating upfront costs and offering near limitless scalability, public clouds have become the de facto deployment method. And the way that they achieve this is through resource sharing. Resources are provisioned onto shared underlying infrastructure, and those resources are reused once cloud tenants no longer need them. However, as we've seen in the past, this resource sharing is not without downsides. Existing works have shown that memory, compute, and storage sharing can cause vulnerabilities when used in this shared setting. However, what we wanted to explore was how the specific resource lifecycle of public clouds, i.e. resource reuse, could have negative security implications. And what we found was that this resource use could represent a real vulnerability. Consider the following scenario. A tenant configures resources on the public cloud and assigns them IP addresses, and they create configuration that causes clients to connect to those resources. This also establishes a trust association with the resources. Next, when a tenant no longer needs the resources, they release them back to the cloud provider, and the same IP address can be given to another tenant. If the original tenant no longer or is unable to remove configuration or does not properly remove configuration that refers to the address, we say that that configuration is latent. Clients will continue to connect to the address because of it. If an adversary receives that IP and attempts to receive the data, the sensitive data intended for that address, intended for previous tenants, they're said to be performing a cloud squatting attack. In order to measure the prevalence and severity of cloud squatting, we deployed a custom internet telescope to Amazon Web Services for over 100 days in 2021. The system is as follows. Note that although we use Amazon Web Services terminology here, the system and the implications are generalizable. We deploy EC2 instances to Amazon's public cloud and have TCP handlers that collects traffic on all ports. It does preliminary analysis of this that needs to be done in real time, and then also records the traffic for use in future analysis. Clients connect to these addresses and send data, potentially data intended for previous tenants. Next, in order to gain high coverage of AWS's cloud, we scale this up using a spot fleet across a variety of availability zones, including 3 million servers provisioned throughout the study in Amazon Web Services US East 1 region. As a result, we received over 500 million network sessions spanning half a terabyte of data. We store this data encrypted in an Amazon S3 bucket and then download it for future offline analysis. Through this analysis, we found that we received over 1.5 million unique IP addresses from the cloud, each studied for a period of time. And, as we'll see in a little bit, this is over 56% of the available IP addresses in the pool. Now, unlike existing works that primarily focus on DNS, we study the effects and configurations referring to IP address reuse directly. And so we discover a new dimension of vulnerabilities across different types of configuration, as we can see in the stars in the figure. As a result of our study, we found that cloud squatting is prevalent and in some cases causes highly exploitable latent configurations. We saw cloud services and third-party services as novel sources of latent configurations in our study. For cloud services, we found over 5 million messages received by our telescope intended for other tenants across 4 different cloud services. On third-party services, we received over 3 million messages potentially intended for other tenants across numerous services such as databases, caches, and other APIs. Finally, we used the domain name system to attribute a subset of these vulnerabilities to specific organizations, finding that over 5,400 organizations were potentially vulnerable, including 23 top 1,000 websites in our study of just one region of one cloud provider. The types of data that we received as a result of this study were diverse, but they included several classes of sensitive data, including financial, personal, and location data, credentials and user-uploaded images, and in some cases, the ability to execute code in privileged positions on customer machines. Let's look at how we measure IP address reuse from the bottom up. As we said, we first provision servers and collect traffic. Next, we hypothesize various configuration types, create filters and run those filters to identify traffic referring to those configurations, and identify vulnerabilities and vulnerable parties. Before we move on to configuration types, let's discuss a little bit more about our data collection. Now, because we'd like to characterize IP address reuse directly, we need to understand a little more about the IP pool. To do this, we take advantage of the scale of our experiment. Because we provision so many servers, it's an inevitability that we receive the same IP address from the cloud provider multiple times. In order to analyze this, we measure the time period between when we receive the same IP address multiple times. This time between reuse is shown in this histogram. X-axis is hours between reuse, and y-axis is number of instances where we saw that behavior. Zooming in on this, from this graph, we can see that IP address reuse follows a Poisson process, showing that IP addresses are pseudo-randomly sampled from the pool of available addresses. Subsequent conversations with Amazon confirmed this. Zooming in on the first bin of this histogram, we can see that IP addresses can be reused by the cloud provider across tenants in as little as 30 minutes after they're released, meaning there's little time for tenants to correct latent configuration before adversaries can receive the associated IP address and exploit the traffic. Next, we wanted to understand the size of the IP pool and how easily an adversary could cover the pool. To do this, we used an open population estimate technique, widely used for wildlife studies, but also applicable here. The statistic gives us an estimate of the number of IP addresses in the pool throughout the study period, and also an estimate of the percentage of those IPs that our telescope was able to observe. As a result of this, we find that we observe over 56% of the total IP addresses available in the pool, and an adversary could do similarly. This leads us to a couple of conclusions. As we saw, the pseudo-random nature of allocation allows adversaries to easily gain high coverage of the pool, and there's little time for tenants to correct latent configuration before adversaries can discover and exploit it. Next, let's look at the configuration types that we studied in our measurement. Now, as we said, clients reference configuration to know which IP addresses to connect to, trust, and send data. And this configuration can take multiple classes that we studied. The first is cloud service traffic. Cloud services are managed offerings by the cloud provider, and while they don't run on tenant machines, they can be configured to connect to tenant IP addresses. For instance, Amazon's Simple Notification Service, or SNS, automatically delivers messages to subscriptions to HTTP endpoints on IP addresses. Next, we have third-party services. Third-party services can be any client software, service, or device that connects to IP addresses due to configuration. For instance, we saw web servers connecting to our IP addresses and attempting to access databases, where they would either send or attempt to receive sensitive information. Finally, we use configurations pulled from the domain name system to attribute a subset of these vulnerabilities to specific organizations. Let's start by looking at cloud services. Now, what we'd like to do here is filter traffic to that sourced from cloud services. And to do that, we take advantage of a couple of unique properties of cloud service traffic. The first is that this traffic is sourced from an Amazon or cloud provider verified IP address. And so we can filter to these IP addresses in a sound way. Next, we can identify the service and associated tenant from HTTP headers. And an adversary could do likewise to discover which tenants they'd like to exploit. Based on these filtering techniques, we discover 4 different cloud services that leaked sensitive data intended for other tenants. For example, we received financial, personal, and location history. In one case, a government social services organization leaked sensitive data over SNS to our telescope, including personally identifiable information about their users, i.e. anything on a driver's license, and real-time location history from vulnerable users. In another case, CloudFront endpoints delivered requests for JavaScript files. Responding to these requests would allow an adversary to run data in a privileged fashion on popular websites. Next, let's look at third-party services. Now, unlike cloud services, third-party services are as diverse as those deployed on the cloud provider itself, and the configurations used in these services are likewise diverse. They can be as complicated as a distributed configuration management system such as Kubernetes, or they could be as simple as a sticky note on an employee's monitor saying which IP address to connect to upload invoices. Because of this, our analysis needs to be general. The goal here is that we'd like to filter out illegitimate or scanner traffic and analyze the remaining share, which is likely to be legitimate. To achieve this, we take advantage of a series of filters that operate at various levels of the protocol hierarchy. Now, due to the scale of the data we collected and the generality of our needed analysis, this required the development of new traffic filtering techniques that were sensitive to this specific measurement scenario, as we'll see. The first step that we took was network filtering using publicly available and vetted IP block lists. This eliminated a majority of the traffic. Next, we performed transport filtering, taking advantage of the unique characteristics of our cloud measurement. Because we receive and measure data on so many IP addresses, it is an inevitability or a near inevitability that scanners in scanning providers will access multiple IP addresses in our telescope over the course of the study, or multiple ports. And so, we can take advantage of this. The figure on the right is a histogram, on the x-axis being number of IPs contacted and y-axis number of ports contacted of all of the connections seen throughout our experiment. As we can see, the vast majority of connections come from IP addresses that contacted a large number of IPs or ports on our telescope. And so, by filtering traffic to just the bottom left corner of this histogram, we can eliminate a vast majority of scanner traffic. Next, we filter at the session and application layers using existing network intrusion detection systems such as Snort and custom rules that are designed to eliminate other exploit, illegitimate, and uninteresting traffic. As a result of these filtering steps, we identified a wide variety of third-party services delivering sensitive data to our telescope and potentially to adversaries. As we mentioned, we saw database and cache traffic, but we also saw financial service traffic, logging, analytics, and advertising networks, and other APIs. In the case of financial traffic, for instance, we saw connections utilizing the Financial Information Exchange Protocol, which underpins stock and other equity markets. We saw logging and analytics data containing personally identifiable information of mobile app users and device credentials, or rather device metadata. We also saw other APIs and webhooks. These allow services on the internet to communicate with each other. For instance, we saw instances of one source control management platform delivering metadata on private source code and credentials to CI servers. In another case, we saw a retired endpoint used by web browsers to get search results or search suggestions, and these contain potentially sensitive private browsing data. As you can see, the services or the configurations we saw under third-party services were diverse, but the result was the leakage of highly sensitive data. Finally, we'd like to attribute vulnerabilities to organizations using the domain name system. To do this, we pulled banner information from requests that identified it, such as HTTP or TLS traffic. As a result, we found over 5,400 vulnerable domains, including 23 top 1,000 websites. In many cases, these domains had several or even over 100 vulnerable subdomains, showing that the problem is both broad and deep across these organizations. In our sample, we saw a wide variety of affected organizations across both industry, academic, and government settings. And, as we can see from the data, even organizations with security subgroups aren't necessarily immune. Naturally, in seeing our findings, our first step was to disclose our results directly to Amazon and other cloud providers. And the vast majority of our disclosure process was coordinated through Amazon in order to achieve the highest coverage. In fact, Amazon took additional steps, as we'll see later. However, we also directly reached out to a select group of tenants and performed disclosure interviews and surveys to reveal root causes, which we found broadly fell into 3 categories. The first is issues with integration, what we refer to as lift and shift. Lift and shift is the technique of taking existing on-premises infrastructure from data centers and moving it to a public cloud provider. Often, this brings with it the assumptions of the private data center, including lack of consideration for service decommissioning. Next, we saw failure to manage integration or failure to manage configuration and lack of oversight. In this, we saw that many organizations lacked a centralized overview of their cloud infrastructure, where many subunits of the organization would have their own cloud presences. In one case, an academic institution had over 100 suborganizations with independent cloud infrastructure. And as a result, it's difficult to enforce best practices such as decommissioning considerations on those suborganizations. Finally, we saw insufficient, lack of, or broken automation. Here, we saw organizations manually deploying instances to the cloud and failing to consider decommissioning, or we saw custom or bespoke deployment strategies that also did not consider decommissioning. This brings us to our defenses and mitigations that can be taken against this issue. Now, as we saw, cloud squatting results from a combination of resource reuse and latent configuration. And so our defenses mirror this taxonomy. In our paper, we discuss and introduce a variety of new defenses that both cloud tenants and providers can take to protect customer data. However, the strategy that I'd like to talk a little more about is IP allocation policy. We hypothesized that by changing the way that IP addresses are allocated on the public cloud, providers could greatly reduce the ability of adversaries to measure the pool. And so we created a new technique which we call IP tagging. IP tagging uses heuristics to automatically segment the IP pool across tenants, reducing tenants' ability to measure new IP addresses. Based on the metrics that we measured in our initial study of cloud providers, we created a simulator that simulates IP address allocation in a virtual public cloud. As a result of this, and analyzing our new technique, we see that IP tagging vastly reduces the number of unique IPs observable by an adversary, protecting user data, among other benefits. In addition to the defenses that we propose, Amazon has taken actions to protect users on their cloud platform. They've introduced new configuration alerts on the console that will automatically alert users when creating configurations that could become latent, such as direct references to IP addresses. They've also taken our findings and performed scanning and disclosure process using control plane information across all regions. Whereas our study looked at one region of a single public cloud provider, Amazon's scanning of control plane information revealed that similar problems exist across all regions, showing the problem is general. They also introduced automated policy enforcement, allowing organizations to enforce best practices from the top down. Further, they document these practices using new documentation to introduce IP hygiene. Cloud squatting represents a serious and widespread vulnerability for infrastructure deployed on the public cloud. Our measurement study found that latent configuration vulnerabilities were widespread across a wide variety of services. Further, existing cloud services may not sufficiently protect user data. Cloud squatting is also deeply practical for an adversary. Because IP addresses are allocated pseudo-randomly, adversaries can easily sample the pool with high coverage. For instance, our measurement study, which covered over 1.5 million unique IPs from a major cloud provider, was performed at a cost of only $2,000. Finally, this vulnerability generalizes to other providers. In our paper, we analyze how the other offerings could be vulnerable. However, there is hope. Cloud squatting can be prevented via judicious configuration management and reduction of IP address reuse. Thank you for your attention, and thank you to the National Science Foundation for funding this work. With that, I'll take any questions.
Thank you very much for the presentation. Do we have questions from the audience? Yes, please go ahead.
Hey, thanks for the talk. I've got a question. So you've mentioned a couple of pretty concerning communications that you weren't intended to see, including financial information. Was this a common occurrence, or do you just find a couple examples of these?
So in some cases, we can definitely sort of categorize the prevalence here. In the case of domain name, for instance, we saw the 5,400. In the case of cloud services, we can look at the number of tenants or number of IP addresses that were vulnerable. As you may have seen in the figure, that was over 23,000 IP addresses for SNS, for instance. So that would be a widespread vulnerability. In the case of third-party services, it's a little more difficult to quantify. However, sort of anecdotally, we saw that this was a large number of affected organizations.
Got it.
Thank you.
Hi, Eric. A great talk.
Thank you.
So one of the defenses that you showed basically says that you can just use IPv6, which I would think is the most practical solution to this situation. But given that there are so many deployment issues with IPv6, it's not being deployed very quickly. So what are your thoughts about that defense? Because with IPv6, you basically do not need to reuse an IP address ever. The address space provided to one host is /64, which is practically just unlimited. So why not just go to that instead of defenses like IP tagging or something like that?
That's a great question. So we see IPv6 as having sort of two realms, one in which it's applicable and one in which, for legacy reasons, it won't be fully applicable anytime soon. For internal service traffic, traffic between services owned by a single tenant, where IPv6 can be deployed across the entire cloud presence, IPv6 is a really compelling solution there. Most cloud providers now support IPv6 endpoints, so if you can do all your routing over IPv6, that'll solve a lot of your problems. However, for public client-facing services, I do agree that we're sort of stuck with IPv4 routing now, so that's why these other solutions, especially the solution of IP tagging, because it is fully backwards compatible, sort of offers a compelling contribution.
All right. Thank you.
Thank you.
So I have a curiosity actually. I don't know if you mentioned it, but how much time did it take roughly to conduct the study? And also, I'm curious about a little bit about the reaction of the cloud providers and maybe the response time in taking actions or responding to you. Yeah.
Mm-hmm. Yeah. So the period of the study is sort of somewhat indefinite. For the initial data analysis, as part of this presentation and the paper, we performed the study over, I believe, about 107 days. In terms of cloud provider reactions, we've been very, very pleased with, especially Amazon's reaction in terms of sort of, responding to us, reaching out with them, and implementing new best practices. In terms of the total measurement study, collection is actually sort of ongoing, and we're continuing to see new and interesting trends in this space. And the sort of in situ cloud provider internet telescope strategy is also potentially leading to new insights in other spaces.
We have a question from home. Our time is up, so maybe if you could go to hop in and answer that, it would be great.
Absolutely.
So let's thank our speaker again.